I am Adam from RFOXiA from our real lab. Today we are answering one question: why has professional long-range wireless hardware cost $5,000 for 30 years, and what changed? Let me start with a number, $5,000. That is the entry price for a professional long-range wireless communication system if you go to the commercial market today, not a research prototype, not a classified military contract, the commercial off-the-shelf available to order price for hardware that does what RFOXiA's BLE module does. In some cases, the number is significantly higher. Tazink's enterprise drone link systems are priced between $3,000 and $15,000 depending on configuration. DTC's Blue SDR platforms start around $5,000. These are not exotic, they are catalog items. The physics behind them is not proprietary. The components they use are in many cases manufactured by the same foundries that produce components costing a few dollars each. So the first question worth asking is not how RFOXiA made something affordable. The first question is why it was expensive in the first place. The answer is a combination of three things: market assumption, engineering approach, and certification cost. And the most interesting of these is engineering approach, because this is where the conventional solution and the correct solution diverged most sharply. For the last 2 decades, the dominant engineering response to range limitation in wireless systems has been amplification. If your signal is not reaching far enough, you increase transmit power, you add a power amplifier, you increase the output wattage. This is intuitive. It matches how most people think about communications. Speak louder if you want to be heard farther away. It is also, in many cases, the wrong answer. Here is why. Increasing transmit power has 3 consequences that compound against each other. First, it increases power consumption. A radio system running high output power requires more energy, which means larger batteries, heavier platforms, reduced flight time on a drone, reduced field endurance in a deployed sensor. Second, it increases regulatory complexity. Most unlicensed spectrum, the spectrum a builder can actually use without filing for a license, has strict transmit power limits. Pushing beyond those limits either puts you into licensed spectrum, which requires regulatory approval, or into legal violation. Third, and most relevant to cost, high power amplification requires specialized components, thermal management, and antenna systems that are expensive to design, manufacture, and certify. The military wireless systems priced at $5,000 and above have in large part been designed around power amplification as the primary range extension strategy. They work, they are effective, they are also built into a cost structure that assumes a customer with a defense procurement budget. Now here's the question I asked instead: what if the transmit side is not the constraint at all? What if the actual constraint is on the receive side? Receiver sensitivity is the measure of the weakest signal a radio can detect and still decode correctly. It is expressed in dBm. Decibels relative to 1 milliwatt, and the more negative the number, the weaker the signal the receiver can hear. A commodity Bluetooth module from a standard supplier has a receiver sensitivity somewhere around -90 to -96 dBm. The chip in the Multinav Pro Plus BLE module has a receiver sensitivity of -104 dBm. That 8 decibel difference is not a small gap. In RF engineering, every 6 dB of sensitivity improvement roughly doubles the effective communication range under free space conditions. 8 decibels is more than a doubling. It is a range multiplication of approximately 2.5 times from the receive side alone before any change to transmit power, antenna design, or any other variable. When you combine that receiver sensitivity with an optimized RF front end and an external amplifier stage, the range numbers change dramatically. Ground to ground between 2 handsets, 5 kilometers, man to drone with 1 module in the air, 15 to 20 kilometers, drone to drone with both modules elevated and ground reflections eliminated, 50 kilometers, on unlicensed Bluetooth spectrum at 2 megabits per second data rate, powered from a battery that fits in a drone frame. The cost of the chip that enables this receiver sensitivity is not $5,000, it is not $500. The STM32WB07 is a production component available through standard electronics distributors. The engineering challenge was not finding an exotic part. It was asking the right question about which part of the link budget to optimize. The second factor in the price gap is certification. FCC certification for a wireless device requires laboratory testing, documentation, regulatory filing, and ongoing compliance. For a well-resourced company with an experienced regulatory team, this process costs between $5,000 and $15,000 per device. For a small team or a solo founder, the same process costs more because the learning curve and the mistakes are part of the expense. RFOXiA has FCC certification on all 4 modules: the BLE module, the GNSS module, the sensors module, the power kit. Each of those certifications represents real cost and real engineering discipline. They also represent the credential that makes the hardware usable in professional deployments, the thing that separates a module you can actually sell and deploy from a prototype that works in the lab and nowhere else. The third factor is market assumption. Military and enterprise wireless hardware is priced for its market. A defense contractor or a large industrial operator expects to pay $5,000 for a communication system the way they expect to pay $200 for a standard cable. The price is calibrated to that is the engineering case for why the price gap exists and how receiver sensitivity closes it. Now let me show you the actual hardware. This is the range claim in hardware form: 50 kilometers drone to drone, 5 kilometers ground to ground on unlicensed Bluetooth spectrum, no towers, no internet, no license required, 1 module, $59 for 2. 2 megabits per second is not a slow trickle of telemetry. It is enough to stream real-time control data, sensor readings, and positional updates simultaneously without the link becoming the bottleneck. At 20 kilometers, that data rate holds. The STM32WB07CCV6 is the processing core that manages the BLE stack and runs user applications simultaneously. This is the same class of chip used in professional embedded systems. It is not a simplified hobbyist variant. Full programmability via SWD is standard. 57 by 47 millimeters. That fits inside a drone frame, a robotics enclosure, or a field sensor housing without a redesign. The mounting holes are standardized. The antenna extends to 140 millimeters. Compact is not a compromise here. It was designed in. The 4 interfaces, GNSS, sensors, motors, and battery management and programming, are not generic headers. They are designed to mate directly with the other MultiNav Pro Plus modules. The ecosystem connects without adapter boards or custom wiring. The RFOXiA Connect app displays live GPS position, sensor data, and provides a PS5 style control interface from a standard smartphone. The range the app operates across is determined by the BLE module beneath it, up to 20 kilometers completely without internet. BLE chat removes the infrastructure dependency from communication entirely. Text, data, and voice between RFOXiA module users over the same long-range BLE link. No cell tower, no satellite subscription, no connectivity required beyond the modules themselves. Full open source access means the firmware is yours to modify. SWD programming access means you are not locked into a fixed application. Whatever the deployment requires, the module can be reprogrammed to do it without a closed ecosystem in the way. The integrated RTC crystal provides accurate timestamping independent of GPS lock or network sync. For sensor logging, synchronization between multiple deployed nodes, or time-critical control applications, precise timing is built in, not added later, not to the bill of materials. When the assumed customer has a different budget, the assumed price changes. RFOXiA was built for the customer the industry ignored: the drone builder, the field researcher, the robotics engineer, the IoT developer working without a defense contract. For $59, the MultiNav Pro Plus BLE module delivers professional-grade long-range wireless performance that was previously locked behind $5,000 military systems. That gap is not explained by physics. It was always a choice.